Hi students, in today's class we shall solve a numerical problem on the line to line fault analysis. We have a 30 MVA 11 kV generator. Its positive sequence and the negative sequence impedance equals J 0.2 per unit. Zero sequence impedance is J 0.05 per unit. A line to line fault occurs at the generator terminals. We need to find out the line currents and line to neutral voltages or the phase voltages. During the fault condition, it is given that the generator neutral is solidly grounded and the generator is operating at the no load condition and at the rated voltage before the occurrence of the fault. Let me write the parameters here. We can choose the base MVA equals 30 MVA. And the base kilovolt kVB equals 11 kV. The rating of this generator is taken as the base values. Z1 equals Z2 equals J 0.2 per unit. And zero sequence impedance equals J 0.05. Here the fault impedance is not given in the question. So the fault impedance can be taken as 0. The neutral is solidly grounded, so Zn is also equal to 0. These are the parameters given in the question. In the last class, we solved a single line to ground fault analysis for the same problem. In this session, we will solve the line to line fault analysis. This is the approach we are using to solve asymmetrical faults. First, we need to draw the sequence network. After choosing the base values, we need to draw the sequence network. From the sequence network, we need to find out the sequence currents and the sequence voltages. So sequence currents and the sequence voltages are to be found out from the sequence network. After we get the sequence voltages and sequence currents, we have to convert the sequence quantities into phase quantities. So convert sequence currents into phase currents using our matrix equation. Similarly, we convert the sequence voltages into phase voltages using the matrix equation. So this is the approach we are using to solve asymmetrical faults. So first we will draw the sequence network. Let me draw the sequence network for a line to line fault. In the line to line fault, we have positive sequence network and the negative sequence network in parallel connection. This is the positive sequence network in which we have a voltage source and a positive sequence impedance. This is the positive sequence network of an alternator. The current is IA1. The positive sequence voltage VA1 equals, let me write this as EA. EA minus the drop IA1 Z1. Let me draw the negative sequence network of alternator. In the negative sequence network, there is no voltage source. We have only the negative sequence impedance, Z2. The negative sequence current is IA2. So this voltage is, there is no source EMF in the negative sequence network. So 0 minus this drop, IA2 Z2. This is the negative sequence network of an alternator. In the case of line-to-line fault, these two networks are connected in parallel through the fault impedance. So these two networks are connected in parallel for a line-to-line fault. This is our fault impedance. In our case, the fault impedance equals 0. So there is no fault impedance here. As the fault impedance is not given in the question, we can assume that ZF equals 0. So this is the network. There is no zero sequence network for a line-to-line fault. Look at the currents, IA1 and IA2 are opposite to each other. And VA1, the positive sequence voltage, and the negative sequence voltages are equal. They are connected in parallel. Now let us find out the sequence currents. Once you draw the network, then you find out the sequence currents and the sequence voltages. From the network, what is IA1? What is the positive sequence current? The current flowing through this network equals the total voltage divided by total impedance. The total voltage is EA divided by the total impedance is Z1 plus Z2. This is equal to, this voltage can be assumed as 1 angle 0. 1 angle 0 per unit divided by Z1 plus Z2. The impedance is J0.2. That is J0.2 plus J0.2. As this voltage, as this phase voltage is assumed to be equal to 1 angle 0 per unit, whenever you have to convert the per unit voltage back into actual voltage, the per unit quantity should be multiplied by the base phase voltage. As the phase voltage is assumed to be equal to 1 angle 0 per unit or 1 plus J0. 1 angle 0 is same as 1 plus J0. Whenever the per unit voltage is to be converted into actual voltage, you multiply the per unit voltage by the base phase voltage. This base voltage is line voltage. In the case of a three-phase problem, the voltage given in the question will be the line voltage. So this base voltage is the line value. The phase voltage is 11 divided by root 3. So you have to multiply the per unit voltage by 11 by root 3 or the base phase voltage in order to get the actual voltage. So this IA1 equals minus J 2.5 per unit. And from this network, you know, IA1 and IA2 are opposite to each other. So IA2 equals minus IA1. So this is equal to J 2.5. and IA0 equals 0 because there is no zero sequence network in the case of line to line fault. So we got the sequence currents. Our next step is to find out the phase current using the matrix equation. This is the equation we are using: IA, IB, IC. This is equal to, the transformation matrix is 1, 1, 1, 1 alpha square alpha, 1 alpha alpha square into the sequence currents IA0, IA1, IA2, and this is equal to, let me write the values of alpha and alpha square here. So this is 1, 1, 1, 1. Alpha square equals 1 angle 240. 1 angle 240 degrees. And alpha equals 1 angle 120 degrees. It is 1. Alpha equals 1 angle 120 degrees. It is 1 angle 240 degrees into IA0 equals 0. IA1 equals minus J 2.5. IA2 equals J 2.5. We will write the values here. IA, IB and IC we can write it here. What is IA from this equation? IA equals 1 into 0 plus 1 into minus J 2.5 plus 1 into J 2.5. 1 into 0 plus 1 into minus J 2.5 plus 1 into plus J 2.5. And this is equal to 0. So the phase current IA equals 0. What is IB? IB equals 1 into 0 plus 1 angle 240 into minus J 2.5. 1 angle 240 is same as minus 0.5 minus J 0.866. 1 angle 240 is in the polar form. This is in the rectangular form. Into minus J 2.5 plus 1 angle 240 into J 2.5. 1 angle, this is 1 angle 120. 1 angle 120 is same as minus 0.5 plus J 0.866 into J 2.5. And this is equal to minus 4.33 per unit. Minus 4.33 can also be written as 4.33 angle 180 degree. So this is our B phase current. 4.33 angle 180 degrees. Now let's find out the phase current IC. IC is equal to 1 into 0 plus 1 angle 120 into minus J 2.5. 1 angle 120 equals minus 0.5 plus J 0.866 into minus J 2.5 plus 1 angle 240 into J 2.5. 1 angle 240 equals minus 0.5 minus J 866 into J 2.5. And this is equal to 4.33, or we can write this as 4.33 angle 0. Let me write the value here, 4.33 angle 0. So these are the three phase currents, IA, IB and IC. These are in per unit quantities. We need to convert this per unit currents into actual current. As you know, actual current equals this per unit current into base current. Now let's find out the base current. The base current IB equals MVAB into 10 raised to 3 divided by root 3 into KVB. This is equal to, this is the formula we are using, S equals root 3 VL IL. S is the apparent power, volt amperes. This is equal to root 3 into voltage into current. Here this is in mega, this is in kilo. To convert this numerator into kilo, it is multiplied by 10 raised to 3. So this is equal to 30 MVA divided by root 3 into KVB equals 11. And this is equal to 1574.6 amperes. This is our base current. Now let's find out, or we can convert this per unit currents into actual currents by multiplying it with the base current. This is the base current. Let me write this as I base, so that we will not get confused with this phase current IB. IA equals 0. What is IB? IB equals 4.33 angle 180 into the base current, 1574.6. So IB equals 6818 angle 180. This is our B phase current. And C phase current equals the per unit current into the base current. And this is equal to 6818 angle 0. So these are the phase currents. Now we need to find out the phase voltages. For that we should know what is the sequence voltage first. Let us find out the sequence voltages. The sequence voltage VA1 equals EA minus IA1 into Z1. EA equals 1 angle 0 minus IA1 into Z1. IA1 equals minus J 2.5 minus J 2.5 into Z1. Z1 equals J 0.2. So VA1 equals 0.5 per unit. VA2 equals minus IA2 Z2 minus, or IA2 equals J 2.5 J 2.5 into Z2. It is J 0.2. This is equal to 0.5 per unit. So VA1 equals VA2 equals 0.5 per unit. And as you know, VA0 will be equal to 0. We do not have any zero sequence network here. In the case of line to line fault, we have only positive and negative sequence network. Now let's convert these sequence voltages into phase voltages using the matrix equation VA, VB, VC. And this is equal to, our transformation matrix is 1, 1, 1. This is 1 alpha square alpha. It is 1 alpha alpha square into the sequence voltages VA0, VA1 and VA2. Now we can write the values of alpha and alpha square here. This 1, 1, 1. Alpha square is 1 angle 240. This 1 angle 240. Alpha is 1 angle 120. 1 angle 120. This is 1 angle 240. Into VA0 equals 0. VA1 equals 0.5 per unit. VA2 equals, this is also 0.5 per unit. These two voltages will be equal because they are connected in parallel. The positive and the negative sequence networks are in parallel. So let's find out the values here. We can write the phase voltages here. So VA equals 1 into 0 plus 1 into 0.5 plus 1 into 0.5. And this is equal to 1. It is 1 per unit. And VB equals 1 into 0 plus 1 angle 240 into 0.5. 1 angle 240 is in the polar form. Its equivalent rectangular form is minus 0.5 minus J 0.866 into 1 angle 240 into 0.5. Plus 1 angle 120 into 0.5. 1 angle 120, this 1 angle 120 equals minus 0.5 plus J 0.866 in the rectangular form into 0.5. 1 angle 240 into 0.5 plus 1 angle 120 into 0.5. And this is equal to minus 0.5 per unit. It is minus 0.5 per unit. Now let's find out VC. VC equals 1 into 0 plus 1 angle 120 into 0.5. 1 angle 120 equals minus 0.5 plus J 0.866 into 0.5 plus 1 angle 240 into 0.5 minus 0.5 minus J 0.866 into 0.5. And this is equal to minus 0.5 per unit. Let me write the value here. So these are the phase voltages in per units. We need to convert this per unit quantities into actual voltages. For that we should multiply this per unit voltages by the base phase voltages. Because in this problem we have chosen the reference voltage equals 1 angle 0. Actually this is a phase quantity. As the phase voltage is taken as 1 angle 0, whenever you have to convert the per unit quantity back into actual voltage, you should multiply the per unit voltage by base phase voltage. So what is VA here? It is 1 into the base phase voltage is 11 by root 3, because the line voltage is 11 or the base line voltage is 11 kV. So the base phase voltage is 11 by root 3. So this is equal to 6.35 kilovolt. And VB equals minus 0.5 into 11 by root 3. And this is equal to minus 3.175 kilovolt. And VC is equal to minus 0.5 into 11 by root 3. This is equal to minus 3.175 kilovolt. So these are the phase voltages. Now if you want to find out the line voltages, what is VAB? VAB equals VA minus VB. So similarly we can find out all the line voltages. So this is the approach we are using here. After choosing the base quantities, we draw the sequence network for a particular asymmetrical fault. Then from the sequence network we find out the sequence currents and the sequence voltages. Then using the matrix equation we can convert the sequence currents and the sequence voltages into phase currents and the phase voltages. So we'll be getting the phase currents and the phase voltages in per unit quantities. Finally, we should multiply the per unit quantities by the base quantity. So we'll get the actual voltages and the actual currents.